what I did here is I took some of the data, but not whole, from the Excel file I used on the first day where we looked at exam scores. Okay. So I have, let's see, I guess I have 19 values here. These are exam scores from some way back class, probably in algebra, something like that. Okay, now. How do we create a stem plot? Or a stem and least plot? Okay, the first thing I think I'll do is I'm going to order these numbers in numerical order. And I can do that by selecting all of these cells. All right, and then I do a sort from the smallest to the largest. Okay, now, what I'm going to do is, for the purposes of creating a stem plot, I'm going to round all values that have a half upward. Okay, it's just a choice. You don't have to do that. You either have to round it up or down, but I'm just going to round it up. Okay, now, a stem is created from the most significant digit. The most significant digit in this case, except for the last, would be tens. So, you see in this number here, 86, the most significant digit 8 represents 8 tenths. So the most significant digit is the tens. I'm treating the units position as the least significant. In other words, I'm going to be, in effect, ignoring the decimal place or rounding it up. Okay? In fact, maybe that's what I ought to do is recreate this. I think this would work. Aha! But it doesn't do what I want, so I'm going to change that a little bit. The details here are not so important. This is something you can do by hand. So, for example, you see, rather than using 73.5, I'm going to round it up and call it 74. Okay? Now, whoops. I didn't extend it all the way down here. So if you had these numbers, and they're in numerical, you actually don't have to have them in numerical order. It's going to be a little easier for me in that case. But so the most significant digit ranges from 7 all the way up to 10. So this is what I'm going to do. Those would represent the stems. And the stems can go from lower value to higher value or reverse. I think the author does it typically from lower value to higher value. So I'll do the same. So I have 7, 8, 9, and 10. Now, in creating a stem plot, we have to figure out what the stems are. In this case, the stems are the number 7, 8, 9, and 10. And basically that means those numbers times 10. Now, the leaves, if you will, are the next significant figure. So what I'm going to do now is the following. I'm going to be recording the 3, the 3, the 4, the 5, and so forth. to the right of the appropriate stem. So for 70, I'm going to put down a 3, a 3. I have two 73s. I have a 74. I have a 75. That's it. There are no more 70s. Then I have an 81. I'm going to put a 1 there. I'm going to put a 2 here. A 4 here. A 5. A 6. And a 7. And that's the last of the 80s. Now, the 90s, I have a 1, a 2, all right, 2 3s, a 4, I have a 6, and a 7, and then for the stem of 10, I have 1 leaf of 4. So these are what we call the stems. And these are what we call the leaves. Now, what I just created is basically a histogram. Histogram based on the most significant digit, basically the number of tens. And I didn't have to do any fancy work in Excel. I could do this all by hand in a relatively easy way. In fact, I could have started from the raw data, not sorted it, and it wouldn't have been all that more difficult. The first time around, typically, you don't end up with the leaves in numerical order. So if I work with the original data, let's see. I guess I sorted. I guess I sorted both columns. Well, anyway, I guess I can't do that. The point is, I could work with the original data, and my leaves would, if I just wrote them down as I encountered them, they wouldn't be in numerical order. What you would then do is take that unordered collection of leaves over here and rewrite your stem plot so the leaves are in numerical order. All that a stem plot is a way of describing data graphically without having to do a lot of work. This is something that's relatively easy to create by hand, and that was its original purpose, was to create things by hand. Because we live in a computer era, we sometimes think, well, can't we do this on a computer? Well, the answer is, yeah, you can. But this is just a nice way of doing things by hand. Okay? This is, in effect, a histogram turned on its side. And typically, we make these leaves all have the same width so that it properly represents a, or what looks to be close to a histogram. Now, suppose I gave you a 7-leaf plot of that fashion right there. I've actually given you all the data, basically. This means that you have a 73, another 73, a 74, and a 75. I have an 81, an 82, an 84, an 85, an 86, and 87, and so forth. Suppose I ask you to find the median value. Well, basically I've given you the data. In other words, ignoring this, if I gave you this, this is the smallest, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I have an odd number of values. So how would I find the median? So I have 19, that's odd. I add 1 to it. Get 20 divided by 2. I want the 10th number in my list. There are 4, 5, 6, 7, 8, 9, 10. So the 10th value is 87. That's the median. Okay? Now, that's a stem plot, stem and leaf plot. Now, it could be, I might have two data sets. Maybe I have exam 1 and exam 2. A back-to-back stem plot would be on one side I'd have the scores associated with one exam, and I'd do exactly the same thing on the left-hand side for the other. That's what we call a back-to-back stem plot. And the purpose of the stem and leaf plot is to, again, give a simple geometric or graphical representation of our data. Okay, let's talk about dot plots. How would I do that? Well, I'm going to do it in Excel, only because it's a little easier for me to do that. But again, a dot plot can be done basically on a, by hand. And what I'm going to do over here is the following. I'm going to put a 1 everywhere down this column. And what I'm going to do is I'm going to create a scatter plot of these values versus 1. Let me do it now. We'll see what it looks like. And see how I could, in fact, redo this or do this by hand in a relatively straightforward fashion. So I'm going to select the data, and for the X values, I'm just using the scores. And for the Y values, I'm just using 1s. I'm going to try and make this a little bit bigger so that basically between the lowest and the highest scores, I've put a dot on the line associated with an exam. That's basically all that the dot plot is. Now there's a little bit misleading about this in the sense that there's some scores that are repeated twice. So one way of correcting for that is to put a dot. If I have two values, two exam scores, you can actually put one dot here and then another dot above it if you're doing it by hand. You can actually do this in Excel where you take care of the case where you have replications, but it's a little more challenging. I probably want to do that in this case. But this is another way of describing the data that may be helpful in some circumstances. I used to use dot plots actually in looking at scores. This was before the age of computers. Well, maybe not, but just as a way of seeing where the scores fell. And you can do it in a relatively easy way. Yes?
I know we've talked about this, but I don't remember what to do when I click on scatter plot and I just get a blank box rather than the little dialog box.
You right-click and just select
Well,
data.
I'll tell you what, why don't we do this after class? Okay, the thing is, you can really do this by hand, all right? I don't mind, in fact, I'll show you the fancy way after class, where you actually correct for the fact you could have multiple scores, have multiple exam scores for this exactly the same. You probably want to correct for that by putting the dots in a column, if you will. Okay, so that's all there is to a dot plot. And a lot of these things, again, unless you do this repeatedly in Excel, it probably makes more sense to do it by hand. Do a nice sketch of a vertical line, or excuse me, a horizontal line, scale it nicely, and put a dot above every value you have. If you end up having two values the same, put one dot above the other. It's actually a kind of a histogram as well, but again, it's a relatively easy way of representing data. Okay. Let's go back to the median and the quartile. And what I want to do is I want to look at the choir data. Now what I have here is basically a rectangle above the heights, where the height of the rectangle is based on the number of individuals, all right, who have that height. So for example, it looks like there are 12 individuals who have a height of 7. Okay? Now, the median of this data, okay, well, before I go there, what is the area of a rectangle? The area of a rectangle is its width times its height. Okay? Now the width of all these rectangles, it turns out, is 1. We can think of this rectangle is centered at 60 and the next one is 65. So halfway between them, this would be 60.5 and that would be 61.5. So that has a width of 1. Now, how can I find out the median from this chart? Well, one way of thinking about it is as follows. Imagine a vertical line moving from left to right. At some point, I will divide the areas of all these rectangles in half between the left side and the right side. That would be the median value. In other words, you see, right at the moment, this rectangle doesn't have very much area. But as I move, see, I have, on the left I have the area of some of these areas, and on the right I have all these. At some point, the area to the left will be the same as the area to the right. That is, in fact, the median value.
The median of mean.
Median. Median. Now, where's the quartiles? Well, basically I use the same idea, and I move my vertical line until on the left side I have 25% of the area, on the right side I have 75%, and that's actually the first quartile. When I get to 50%, that's either the median or the second quartile. When I get to a point where 75% of the area is on the left and 25% is on the right, that would be the third quartile. Further, when I get to a point where the area, the amount of area of the total is 90% on the left and 10% on the right, that's my 90th percentile. We just had a lesson in calculus, okay, which is what calculus is about. It's about finding, well, that's one of the topics. It's finding areas. In this case, it's relatively easy because we have rectangles and we know the areas of rectangles. Well, in calculus, what you do is you have continuous curves, and are curves that are not rectangular, and you basically use the same sorts of ideas. You extend your notions of area, and the median for a smooth curve, if you will, is a point where you divide the area in half. That's an exact statement, basically. Okay. The problem, or the challenge here, and actually it's not real involved, but it would take us down a side street. How do you figure out? How do I figure out the value from left to right where I've divided the area, say 25% is to the left and 75% is to the right, that would be the first quartile. Well, you have to know the total area, okay? So this would be it would be basically the counts. So it would be the total area here would be 130. So what's 1/4 of 130? 32.5. Okay. All right. So this is 2 plus 6. That's 8. Plus another, what's it? 8. 16. So I get until I get to, if you will, the rectangle where I know that it has to be, the quartile has to be between there. So I just find the line based on proportions, if you will. Again, where I've divided the area underneath all these bars, where 25% of the area is to the left and 75% is to the right. Okay, so that's actually another way of finding quartiles. And you would use this technique when you have the data's already been divided into a frequency distribution. Excuse me. Okay. Excuse me. Let's just go back to the graphics that I had displayed. I didn't have as I recall, I didn't have a lot of time for this. Unfortunately, I don't know, every time I try and display this, it doesn't work so well. It's a little bit involved. And it represents the flow of energy in the United States. This is, if you do a search, a Google search on energy flow or something like this, you'll find multiple hits. This is kind of a popular way of representing how information flows through our economic system. Again, anytime you're talking about the graphical display of information, you have essentially unlimited options. This turns out to be a very nice way of describing it. We think of moving from left to right. These are what are called primary sources. This is solar, nuclear, hydro, and so forth. Most nuclear is used, in fact, all nuclear apparently is used for the generation of electricity. When you generate electricity, most of the energy goes out to stack and heat. And it's just a fundamental problem in physics and engineering. And so of all the electricity that is generated, this is the amount of stuff that actually gets into someone's home or business. And this amount right here represents the amount of energy that goes out to stack and heat. And if someone could improve that, I mean, every time you get a slight improvement, people are just ecstatic. It turns out that natural gas has the potential right at the moment for being the most efficient. There are natural gas plants who are about, I think, maybe between 50 and 60% efficient, meaning between 50 and 60% of the energy that comes in actually goes out through the line in the form of electricity. But if you're talking about nuclear or hydro, I don't know what hydro. If you talk about coal or nuclear, things like that, they're much less efficient. And it's not because they don't want to make them more efficient, they're very challenging engineering problems. Let's see. This one was, again, this is not typically thought of in a way as a graph, but it's a nice way of describing where people are using energy. You can see the eastern part of the United States, the west coast, down here. This is probably Sao Paulo, is that, whatever. And then you can see Europe, the Middle East, and then Japan. So it tells us, it's kind of a graphical representation where energy that is created by humans is used. All right, and of course China uses a lot along the coast, but not a lot on the interior. Looks like India is kind of spread throughout. This would that be Victorious? Yeah, let's see. This is Hawaii. You see there's probably Anchorage up there. This was created probably by the NASA or the Jet Propulsion Lab. And again, you see, if you do a search, a web search, lights at night, you'll see a lot of hits for this. I think I did this one last time. This was created about 1856 by a guy by the name of Charles Minard, M-I-N-A-R-D. The D is silent because he was French, and then usually the last consonant is silent in French. And Napoleon invaded Russia in 1812, and the thickness of this line represents the size of his army. Of course, as he invades Russia, he's incurring casualties, both battlefield and from sicknesses and so forth. I think I said he got to Moscow, didn't quite know what to do with it, hadn't planned for winter, so what does he do? He burns it down, and then decides he's got to leave because he doesn't have any provisions for winter. And on the way out, what you have below here is the temperature in Fahrenheit. And I think I mentioned last time, it gets very cold in Russia. And if you don't have boots on, if you don't have tents and all that sort of stuff, you've got a really good chance of dying of hypothermia. And of course, you can kind of see that on the way out. There was a crossing of one of the rivers, I think, where a lot of the soldiers drowned because they were crossing in boats or maybe on foot, and they broke through the ice, and they simply didn't survive. And of course, this was the size of his army when they left. Okay, armies keep statistics, and there are a lot of conclusions from this, and that is that one would be who won. Well, I don't think Napoleon won. Certainly, Napoleon got out, but his soldiers didn't win. It looks like only about 1/30 of his army left of that which ended. I'm not exactly sure. This became very popular about 20 years ago, and is considered one of the best graphics of all time. This is the concentration of CO2 in the atmosphere, and we talked about the up and down. That's because the biosphere is breathing in and out. It's taking in carbon dioxide out of the atmosphere during the spring, and then in the fall, it breathes it out, it decays. But there's a general increase in carbon dioxide due to our burning of fossil fuels. This is the Arctic sea ice, and it's the extent of the Arctic sea ice which is now being monitored. Of course, the extent of the ice peaks in March. This is the time series. This wasn't the one before. Time series over time. This is again one of those graphs, again, March or January through December, and you see this periodicity, this rough kind of sinusoidal type pattern. Some of these are individual years, some of these years are averages. You see for these two here, I guess the light blue and the black here, you see you don't see quite as much up and down or irregularity. For a given year, you can have a great deal more irregularity. We had apparently a new, as I recall, a new low in September in 2012. And they do this, you can see graphical descriptions of this on the web. Okay, this is the same graph that was used in the text. This is the version they use. This is a little bit better. Florence Nightingale went to Queen Victoria and said, we really ought to do a better job taking care of the soldiers who are wounded in battle. It turns out that this was in, I think, about 1850, when the British, the French, and the Turks fought the Russians in a little country we now, or a little place called Crimea. That's been in the news recently, for those of you who pay attention to that. And what happened is that soldiers that were often wounded in battle went back to the nurse or the first aid stations or the hospitals, and they weren't dying from their wounds, they were dying from all the diseases they contracted in the military hospitals themselves. Florence Nightingale used not this graph, but the one previously in talking to basically Queen Victoria, and said we can do a better job simply by having better sanitation in these hospitals. And she used that graph as a way of convincing Queen Victoria to do that. Now, she was one of the earlier users of graphical methods. This would be a better way. And basically, the blue represents the number of soldiers who are dying from preventable deaths. And so, apparently, sometime around probably March of 1855, somewhere along, she started instituting those procedures. And you can see a dramatic decline in the number of individuals who were contracting diseases in the hospital and dying from them. So we often use these ways of these graphs as a way of conveying information. I like this one. This says how people in 2005 were getting to work, all the various measures. Let's see, is there another? Yeah, this is always a fascinating question. If you're not getting to work by bicycle, motorcycle, taxi, walking, working from home, public transport, whatever, what does the other mean? I don't know, that's a good question. Helicopter? Maybe it's horse. Maybe it is horse. All right. So, but the big problem here is we always drive by ourselves. That's why we use so much energy. This is a time series as a bar chart. I have solar panels on my house. This was in the year 2012, and I wasn't the monitoring began in March of that year. So this is not complete data, but you can kind of see it goes up during the summer, there's more sun, and then it declines during the fall and into the winter. And this was on a particular day, or no, this was in September. Again, a time series. Vertical represents the amount of energy produced. This is the time, this is the day. So apparently it was relatively sunshiny the first part of September of 2012. Apparently it was a cloudy day. And then it bumped back up to normal, and then another cloudy day, and then a very bright day, and then it kind of declined. And it goes from here to here because that's when I captured the date. And then, let's see. This was a specific day on namely June 26th of 2012. We see the up and down. And this was certainly probably a day where you had clouds going over, and then it would be cloudy, and then bright, cloudy, bright, and so forth. When it was bright, you had a lot of power produced, and then it dropped to very low levels, apparently when there was a lot of clouds. And then here, we had, on September 25th, we had mostly a sunny day. Apparently there was one cloud patch that passed around, looks to be about noon. Okay, these are all time series. All right. What we now need to do is we now need to start talking about the standard normal, or the normal model, not the standard. We'll get to the standard normal model in a moment. You may have heard the expression bell-shaped curve before, maybe in one of your social science classes, maybe one of your biology classes. And usually what they do is they have a drawing that looks something like this. In this case, it looks roughly like a bell, maybe a little flattened bell. There is a precise mathematical formula that defines what we call the normal model, or I'll always slip because the statisticians call it the normal distribution. It's useful to describe it as the normal model in the sense that a model is something that is kind of a simplification of reality. I mean, when I was a kid, we had little airplanes we glued together, and we had little trains and cars and so forth. Those are models. They're simplifications of reality, but in terms of their geometry, are a fairly good description of whatever we were looking at. Well, the normal model can be a useful way at times of looking at certain sorts of data. Models are never perfect, they never capture reality exactly, and some models are appropriate in some circumstances and inappropriate in others. The normal models are commonly used model in statistics for a lot of reasons. First of all, there's a lot of theory associated with it, and there are a lot of circumstances where, in fact, it's a useful model, but not always. Okay, now, anytime we talk about a normal model or normal distribution, to be precise or to be specific, I need to give you two numbers. One is represented by the Greek letter, looks like a U, we pronounce it mu. So I need to tell you what mu is, and I need to tell you what this second number is. The symbol here is a Greek letter sigma. So if I tell you what mu and sigma are, I have uniquely identified which model I'm talking about. There's, in fact, an infinite number of models, normal models. To be specific, I have to tell you those two numbers are what we call parameters. The parameters uniquely define which model we're talking about. Now, let me sketch. Actually, maybe not. I know what we'll do. Oh, I don't have to risk by attempting to replicate this. This horizontal line here represents values that we can observe. For example, when we look at neck sizes, remember when I created the histogram, it was roughly symmetric. All right, a normal model would be appropriate in those circumstances. Now, the horizontal line represents some sort of measurement. In the case of neck sizes, it would be the length of your, or the distance around your neck, or the circumference. Now, the peak for a given normal model is always that first number, mu. Now, the significance of sigma is as follows. This is mu. Suppose I go to the right of it, that number of units, sigma. So this right here, we'll call mu plus sigma. And if I go one more, it will be mu plus twice sigma. And then one more, finally, will be mu plus 3 sigma. Usually by 3 sigma, to the right of the center, the curve has come fairly close to the horizontal line. If I mark off the same dimensions on the left, again, these are just approximate. This right here would be mu minus sigma. This right here would be mu minus twice sigma. And this right here would be mu minus 3 sigma. Mu is a kind of a unit of measurement that's useful for normal models. Now let's look at the rule 68, 95, 99.7. For all normal models, the area, which is bounded above by this bell-shaped curve and below by this horizontal line, the area is 1. We can also think of that as 100%. 1 is the same as 100%. Now, if I draw, say, line segments at mu minus sigma and mu plus sigma, this area right here is 68%. That's where this comes from right here. Now, if I measure the area, say between the center, or 2 standard deviations to the left, which means mu minus twice sigma. The area between these 2 line segments here, and we'll do it this way like that, that is in fact 95. That's where this 95 comes from. Get this out of the way so we... All right, finally, the area underneath the bell-shaped curve between 3 standard deviations to the left and 3 standard deviations to the right is 99.7. So when you see the rule, the 68, 95, and 99.7 rule, what that means is as follows. 68% of the area underneath a normal model occurs between 1 standard deviation above, that is mu plus sigma, and 1 standard deviation below. 68% of the area is between those 2 limits. 95% is between 2 standard deviations above and 2 standard deviations below. Between 3 standard deviations below, that is mu minus 3 times sigma, and 3 standard deviations above, that is mu plus 3 times sigma, lies 99.7% of the area. Okay, now, where do those numbers come from? Well, they basically come from calculus. We can describe this bell-shaped curve by a precise mathematical formula, and using techniques of calculus, we can come up with these numbers. All right? Okay, now what we're going to do is we're going to be learning how to work with this normal model, because it's a model that's used repeatedly in statistics. Okay, so with that, let's see what we have on this page. Well, the normal distribution is useful as a model if the histogram of a data set is symmetric and unimodal, which was the case for neck sizes. Okay, so this would be an appropriate model. We'll get to this second bullet in just a few minutes. Now what I've done here is I've shown you actually 3 examples of normal models. Remember, in order to uniquely identify which model we're talking about, I have to give you 2 numbers. I need to give you a value for mu, and I need to give you a value for sigma. Now the blue bell-shaped curve here, the first parameter, or mu, is equal to 0. and the second parameter, sigma, is equal to 1. This is also known as the standard normal model, or the standard normal distribution. This second curve here, the red shape, has a mean, or mu. We often refer to mu as mean. That's because it is it's actually a theoretical mean. It's a population mean. Mu is equal to 5, and sigma is equal to 2.5. That's what I graphed over here. Yeah, 2.5 would be the standard deviation. Now the green, the body green, has a first parameter of 10, that is mu is equal to 10, and a second parameter of 1.5, that's our sigma. Now let's look, these are all bell-shaped, but they have different peaks. The peaks are at different places, and how spread out or how compressed they are varies. In comparing this, the blue with the red and the green, basically their positions along the horizontal is determined by the first number. So the peak of this first normal model is above 0. For the second one, the peak is above 5. And for the third one, the peak is above 10. Now the second number indicates how spread out something is. The bigger the second number is, the more spread out it is. Well, let's look at these curves. This is the least spread out. This is the next least, and this is the most spread out. Here, this is a 1, 1.5, 2.5. The bigger sigma is, the more spread out the bell-shaped is. One way of thinking about these, if I want to get from here to here, what do I do? Is I kind of push this down and then shift it to the right. And pushing this thing down here, I'm kind of spreading it out. If I want to go from, say, here to here, I still would push down a little bit and shift a lot more. In comparison with this, here, in going from here to here, I have to push down a lot. Kind of, if you imagine, if you will, pushing all this area down and keeping the symmetry. If I push down and then shift to the right, I get this. Now these are just 3 examples out of an infinite number of possibilities. The first number, mu, can be either positive or negative. The second number, sigma, must always be a positive number. Okay. Now, anytime we talk about a normal model, if we're going to be able to do any calculation, I have to tell you what is mu and what is sigma. We can do some things without knowing it, but generally speaking, to be concrete, I need to tell you what mu and sigma is. Or are, not is. Okay. Now what I'm going to do is I'm going to do a series of problems in chapter 6 in which we're going to be using these ideas in a particular model. Okay. The question that was asked is, why is the scale from 0.0 to 0.5? Okay. When you have an algebra class and you graph an equation, how much you see of the graph is dependent upon if you're using a graphing calculator or some sort of online graphing tool. How much you see depends upon the scales on the vertical and on the horizontal. In this case, it was convenient for me to use the scale from 0 to 1/2. Convenient in the sense that if instead, okay, let's notice the following. This represents 5 units horizontally, whereas 5 units vertically goes probably roughly to the roof. Okay? So I'm using the dimension, the scales are different. And the reason, suppose I use the same vertical scale that I have the horizontal. So if this is 5, that's 1, and then 1/2. So if I were to use the same scale, vertical scale, you wouldn't be able to see these graphs. Okay. Sigma describes, let's see, in this case, sigma is 1. It's kind of compressed inward. Well, in general, the larger this is, the closer the curve will be to the x-axis. Okay? So if I had another collection of normal models, and all of them were bigger than 1, I wouldn't necessarily have to have a scale from 0 to 1/2 to see them all. Okay? Now, there's no reason why this couldn't be 1/2 or 1/4, and if I were to do so, it would be really even more compressed in and even further up.
So her question was that the mu and the sigma don't relate to the y-axis.
They don't relate in the sense that if I think of my graph as being infinite vertically, and I have a big enough, I can use whatever I want. I chose the 0 to 1/2 out of convenience so we could actually see these graphs. In other words, I wanted this to represent 0 and this to represent 1/2. Because if I were to use the same scale vertically that I have horizontally, my graphs would only extend like that and you could hardly see them. The purpose of kind of expanding this, what I'm doing is I have a magnifier that works in the vertical direction only, so I can see what these actually look like.
The sigma number increase and the graph.
It's more spread out.
More spread out, okay.
So you see the first number indicates where the peak is. And the second number indicates how spread out it is. The bigger the second number is, the more spread out it is. The closer the peak is, if you will, is to the x-axis. Yes?
Wait, did I hear you say that the sigma is standard deviation, the same?
Yeah, sigma. Okay, yeah, this is, welcome to the world of statistics. Sigma is in fact a standard deviation, but it's not a sample standard deviation. It's a theoretical or a population standard deviation. Okay? Now, see, this is the way the normal model works. Let's go back to the Excel file that had the next sizes in it. Let's see here, let's go back. Okay. You know what? I don't think I computed the mean and the standard deviation for this data, so I'm going to do that right now. Okay. For next sizes, the mean is 14.9. That's the sample mean. The sample standard deviation is 0.9075. Notice that the mean is very close to what I previously calculated for the median. For symmetric distributions, the median and the mean are about the same. The mean here and the standard deviation is based on data that I have collected, or that someone collected. In a model, mu and sigma are values that are chosen because we believe somehow that they might nicely describe a collection of numbers. So if I want to talk about next sizes, what would be a convenient choice for the value of mu? That would be 14.94. What would be a convenient choice for the value of sigma? It would turn out to be as 0.90175. Now, if I collected more data, that is, I measured the next sizes of more males, those would change, and I'd probably want to use a slightly different model. But I think this would be probably pretty close. Again, I suspect these were probably college-age males, and if at that time we measured a larger collection, these values probably would not have varied all that much. So, the value of mu and sigma are theoretical values that position where our curve is and how spread out it is. We choose those, if you will, to somehow match, in some respect, the data we're analyzing. Yes?
How do you determine if the median of population is sample?
You have to, well, okay. If I don't tell you where the number 4.94 comes from, you don't know. The fact that I've computed it from data, I know it's the sample mean. Now, I might want to use 15 as my theoretical value. I mean, that's pretty close to 14.9. There may be, maybe there's some reason for doing that, but unless I tell you how I obtained these numbers, you don't know whether it's a sample mean or, in effect, a population mean. And the same thing is true for the standard deviation. Unless I tell you that I got it from data or that I got it from theory, you don't know whether it's the sample standard deviation or the population standard deviation.
But aren't we so close to
Yes and no.
Depends on what you're measuring, right?
Okay. In general, if I have a large amount of data, and I have properly selected the data, which we have not talked about yet, the two values should be pretty close together. How do you properly select data? Well, stay tuned. We'll get to that in, I think it's maybe 9 or maybe 10, something like that. What we would do is we would take a random sample from the entire population, and if we do so, and our sample size is large enough, then the sample mean and the sample standard deviation should be close to the population values, that is mu and sigma, assuming that a normal model or a bell-shaped model is the most appropriate. Okay? These are good questions. It's kind of, the problem in teaching statistics is you don't know where to start. I mean, most stat classes start by analyzing the data that's in play. They don't directly go into theory. Other than that, directly go into theory. Well, theory is a little more challenging. You probably believe that if we have some acquaintance with real data, the theoretical part may make a little more sense. All right. You could approach this initially solely from a theoretical point of view. And if, depending upon, your education, actually some people go that way. I went through the theoretical side first before I got to the real data side, or mostly the theoretical side.
And the theory being that if you have a set of data, then things tend to happen in similar ways.
A theoretical in statistics theory has to do with precisely defined models and precisely defined relationships between that which we sample and that which we are likely to observe. Okay? Okay. So in this case, suppose, let's turn this around. And again, I'm assuming the neck sizes of these males were probably collected from college-aged males. I think was it in Utah they did this? I don't remember the exact details, but suppose at that time, instead of selecting 251 males of this, say, college age, we measured the neck sizes of all males in the United States. Okay? We would have a value of the mean and the value of standard deviation. Those, in effect, would become our mu and our sigma because it's collected over the entire population. When we select only a portion of the population, that's when we have sample data. All right. Let's take a look at some problems. And I think what we'll do is, let me just outline what we're going to do. Then we'll take a break. We'll come back. Let's see, I'm going to start with problem number 26 on page 137. Okay, now, the reason I'm using this problem is not because I like the use of IQ tests. There are lots of issues and debates and so forth about IQ tests. We're going to ignore all that. We're going to live in an idealized world for the moment where the assumptions we make are, if you will, reasonable assumptions. Now, in this problem it says, some IQ tests are standardized to a normal model with a mean of 100 and a standard deviation of 16. So this is what they're saying. We are going to be using a model where mu is equal to 100 and sigma is equal to 16. We summarize that by putting an n followed by 100, followed by a comma, followed by 16. So if you see this, automatically we mean that mu is equal to 100 and 16 is equal to sigma. Now, this uniquely defines a bell-shaped curve where the peak is above 100. So what I'm going to do here is for a moment blank this so I have more space. So what I have if you will, is a model which looks something like that. The peak is about, or is exactly at 100. Now, one standard deviation to the right would be 100 plus 16, so that would be 116, and I'll put that right here. That's 116. Two standard deviations to the right would be 100 plus twice 16, so that would be 132. And then three standard deviations to the right would be 148. Now to the left, one standard deviation below would be 84. Two standard deviations below. If you need to communicate, why don't you write it down? Let me hurry up. I said okay. That's one standard deviation below. Two below would be 68, and then three below, I guess that would be 52. So this horizontal line represents scores on this exam. Basically what this means, or one way of thinking about it, is most people that take this exam are going to get a score close to 100. Maybe above, maybe below. 68% of people taking this exam will lie between these two values. The area underneath this curve is 68% between one standard deviation below and one standard deviation above. 95 will lie between 68 and 132. Okay, and then 99.7 will be between three standard deviations below, three standard deviations above. That's what we're kind of saying in a summary form. Now what we'll do is we'll specifically address the following questions after the break. Well, it says draw a model. Well, I've drawn the model. And I've clearly labeled the standard deviations. I'll put up the 68, 95, 99.7 rules. I'll indicate them graphically. In B it says, in what interval would you expect the central 95% of the scores to be found? I basically addressed that. In C it says above, or about what percent of people should have IQ scores above 116? What is the proportion of individuals who will have a score above 116? Well, basically that's this area here, and from the description I've given you, we can actually figure that out. We'll do that after the break. About what percent of people should have scores between 68 and 84? That is, what proportion of individuals will have scores between 68 and 84? It's nothing more than this area here. All right, and then finally it says, about what percent of people should have IQ scores above 132? That is, what's the proportion over here? Okay, so let's take a break for about 10 minutes. When we come back, I'll address those questions.